This is the PowerPoint for the wearable sensors for heart rate monitoring group. My name is Jailyn and heart disease is the leading cause of death among men and women every year. Around 610,000 people die in the U.S. alone from just heart disease. That's one in every four deaths in the United States that occur. So the quicker the heart disease is detected, the quicker we can treat it and give people a higher chance of having successful treatment for the disease. We want to be able to provide self-awareness for people so they can make changes to their daily lives as far as the stress they take each day and their physical fitness, as far as working out more, eating healthy, and just better ways to take care of your heart. The data picked up from these sensors can be shared with your doctors for them to observe and store away for later dates and appointments that you may have scheduled throughout the year. And creating these sensors, they can provide new skill sets for people to use. They can promote creative thinking, teamwork, and give us a better understanding of the sensors and the components and how they can be used in other applications in life. And yeah.
Hi, my name is Ranye McClendon, and I will be presenting our project goals. Our goals were to create a circuit to detect the heartbeat using a piezoelectric sensor and a microcontroller. Our second goal was to simulate a circuit in Multisim for the prototype in case we needed to troubleshoot any issues before building the actual circuit. Our third goal was to use MATLAB to filter noise and create an algorithm to better detect the heartbeat. Our fourth goal was to develop a mobile app to display data acquired from the sensor. And our last goal was to make the device wearable.
My name is Shane Mann. So in order to figure out how to make this sensor work with the analog discovery or microcontrollers, we had to figure out, first we had to start with what did we already have and what did we need to make this happen, to make it work. So we had two piezo sensors that we could utilize and that we practiced with. So a piezo sensor is stress on the crystals inside create voltage. And so we use that to find the signal or the pulse and somehow eventually establish a heartbeat. So the first sensor we used is the first one on the right there, the little rectangular piezo sensor made by Speccom. It's a 28 micrometer polymer film. Then it's laminated. Then it becomes a 0.125 millimeter object. Its resonant frequency is about 180 hertz. What that means is it will easily pick up a vibration, but it won't exceed 180 hertz, that frequency level. The other one we have is over on the top right corner, as you can see. That one's a little different. It's circular in shape, but it has two different types of material. The white circle on the top, that is made of ceramic. And according to the research, ceramic piezo elements pick up, or they're able to pick up a vibration. Their threshold's a lot larger, as I'll explain here. The disc underneath is brass, so they combine them together. In total, it's about 0.4 millimeters thick. And the reason that I put the sizes up there they're going to relate to how they fit on somebody's wrist in order to detect it. So we had to find a small piezo sensor that that could be incorporated into the device. So the thing about the time STL piezo disc element, its resonant frequency was all the way up to 4.6 kilohertz. So the spectrum or the threshold it was a lot larger. Trying to figure out exactly what the resonant frequency was or how it affected the circuit. Still trying to figure that out. But basically the resonant frequency, each element or object can detect another object's vibration as long as it's easier to pick up if it's within that resonant frequency. It can take a small vibration, i.e. your pulse in your arm or your wrist or wherever the piezo sensor is set, and it can create larger voltage spikes through pressure or vibration. So this allowed us to create, in hopes, was to create a larger voltage spike or pulse, an identifiable pulse with a larger resonant frequency. Some challenges with the piezo sensors were the placement. We found that anywhere you put them, basically, whether it was on your neck, your wrist, you had to apply a lot of pressure in order for the analog discovery to detect or even read or display a pulse. That was a huge challenge. So with that being said, I'll speak on the analog discovery. So analog discovery was was new to me. It's going to be incorporated into my classes, which is awesome. But the features were a challenge, trying to understand all of them. So with the analog discovery, you have a waveform generator, you have an oscilloscope, and you have an alternate power supply that you can send to a circuit. So just figuring out how all that worked was a challenge. In order to understand it, we were introduced to a couple of projects by the grad students. One circuit specifically was a voltage divider. We built a voltage divider circuit and hooked up the analog discovery to that circuit with input from a waveform generator and the power source or power supply. And then the output signal went into the oscilloscope, which you can see on the right there, the big oscilloscope picture. That is not from the voltage divider. That's actually from us hooking up a piezo sensor to the analog discovery, straight to the analog discovery. And so the initial signal acquisition is what we have there. As you can see, it's really noisy. There's no definitive heartbeat, not clearly defined. So from that point, we had to figure out, okay, what are we going to do? How are we going to do this? Research, we started looking around at circuits and how we could narrow or refine or define the heartbeat that we were getting. So, let's see. There we go. All right, so what we come up with was an active bandpass filter. We needed something that was going to filter out the noise, but amplify the output signal, which is what we wanted, which the output signal is going to be the pulse from the sensor. We use this, so we created an active bandpass filter using an op-amp, the LM341. It's a single band, meaning it's only one-sided. It will only create one op-amp. There's other op-amps out there. We just didn't have them or couldn't find them. But this is all we needed. So the op-amp basically would take the signal, which is the op-amp LM341 is an IC chip. So an integrated circuit, small little device, which is what we were going for because we're trying to make this wearable. So we built the circuit. The schematic is up on the top right, and you can see R1, C1, R2, and C2. So what it does is it establishes cutoff frequencies, or basically a bandwidth. And so your heart, an average heartbeat is somewhere between 60 and 100 beats per minute, depending on the individual, their physical fitness and the level of work that they're doing. So at rest, you could assume that the heart would beat about 60 beats per minute. And if you're active, it can go up to 100. So that translates into the frequency that we were trying to pick out. So the average heartbeat or frequency is between 1 and 1.67 hertz. So once we figured out how to do this circuit, build this circuit, we wanted to set the lower filter limit at 0.5 hertz. And the upper cutoff frequency, we wanted to stop at 5 hertz. So what that means is anything above 0.5 hertz would be allowed through the bandpass, and anything below 5 hertz would be allowed into the bandpass. And then that specific signal would be amplified to the output of the analog discovery or microcontroller, as we'll get into in a minute. The problem with this is the active bandpass filter. It's huge. It is basically this circuit here, along with the analog discovery. And as you can see, it's large. So, and that's just a prototype. That's just a prototype. You know, what we're trying to do is just find this heartbeat, find the signal. And we'll get into that here shortly. But one of the other goals or processes that we were thinking was, once we got the circuit, there's programs out there like Eagle, where you can design your circuit on the computer, and then you can have that printable circuit board or PCB made for you and sent back. And you can, for a small fee, obviously, and then you can incorporate it into your platform or whatever creation that you're going to use the circuit in. So after we figured that out, we built that, and we got a beautiful signal, which I will show you in the next slide. So once we got that, we found out the sensors we needed. We established that we needed something to filter out unwanted signals and amplify the signal that we needed. So then we decided the other part of this project was to make it something, collect the data that the sensor received and be able to display it in a graph. So we had on hand the Arduino, so we had to research Arduino capabilities. We needed to find out if we could code the cutoff frequencies, as well as display the readings. So we were able to do those. The only issue that we had is there's a couple challenges with that. Was the Arduino would do the same thing and collect the data, and we were able to store it, but we had to incorporate the active bandpass filter with it. So we attempted that, test and trial, and it worked. It gave us the same readings. However, now we just incorporated something extra. So what we tried to do, the thought process was, well, let's see if we can take this Arduino and utilize it in the same aspect as the filter and get the same results. The thing about the Arduino is we couldn't incorporate the circuit due to the voltage requirements. The circuit we built using the analog discovery needed voltage due to the op amp. So in order for the op amp to actually work, it needs to have power. It needs to be turned on. 5 volts would not do it based on the circuit that we built. So the Arduino incorporated with the bandpass filter wouldn't work. So we took out the bandpass filter, put in a circuit, or just the sensor itself, into one of the analog inputs and ground. And we did get a signal. It did work. The other challenge was the Bluetooth module. So in the coding, we would, well, first for the Bluetooth module, it's an accessory to the Arduino. It doesn't have BLE capability, Bluetooth Low Energy. So now we would have had to add another component on top of that. And it's just, then of course you have to do the coding. So you'd have to code in order to make the Bluetooth hook up and be able to sync with another external source to receive the data. And then the Arduino is just too big. It's not wearable. So we kind of started searching elsewhere. There we go. So if you can see as you can see up on the top right, that is a beautiful display of the analog discovery and the active bandpass filter. So the yellow line is the input signal. The blue signal you see is the output from the op amp into the oscilloscope of the analog discovery. We had, so the yellow line and the blue line, we had two oscilloscope readings. we wanted to be able to see that we were getting an input signal and it was minimal, and also be able to see that we were getting the desired output signal from the circuit, and it worked. It's a very clear signal. You can see the inputs, the yellow line, match up with the output of the blue for each heartbeat or pulse sensed by the sensor placed on our wrist. So analog discovery reduced the noise on the sensor, and it came out great. Bandpass filter. Results with that, as you can see in the top picture, we were able to identify a heartbeat very clearly. And at the same time, using that, we were able to record data from 6 different students. We did 5 samples per each student so that we had various signals so that we could send all that data over to the MATLAB people so they can do their thing and maybe refine it some more. So that was excellent result. We were all pleased with it, and it looks good. So the results for the Arduino and the microbit. As I mentioned before, the code met the conditions. We were able to code both microcontrollers to receive the input and give us an output display within the parameters, which was 0.5 to 5 hertz, 0.5 hertz to 5 hertz. No bandpass filter was required, so it kept the package small. It displayed results, as you can see on the next Arduino picture. You were able to display results, not as identifiable, but using the code, you can see that the threshold was just above, or the filter that we implemented in the code was just above 0.5 hertz. Except it's hard to tell which peak or spike is the heartbeat. And then, like I said, what we also found out with the results is we were unable to transmit data via Bluetooth through the Arduino, and for the microbit, it would require a little more research and coding in order to make that happen. The other result we were able to create a wearable prototype designed in AutoCAD. That's on the bottom there. The case comes apart so you could implement the PCB that I mentioned developing through Eagle. So you could put a small battery in there. you could encase the electronics, and you could place the sensor, either sensor, underneath on the bottom, and a strap through the hole in the middle there that would hold it to your wrist and be able to sense your heartbeat at the end. So one thing I didn't show, or that I would like to show, is the microbit. I didn't have any pictures. I forgot to record. My apologies. But if you can see the microbit, there's a little heart right there. Move out of the way. There's a heart on the top. So when I said that it had an onboard display, this is a wearable device that you can easily incorporate the filter or the piezo sensor with. And if you watch the heart, you will see it get smaller and larger when there's pressure applied to this ceramic sensor. There we go. Maybe. There we go. So each time I tap it, yeah, of course it's not working. You can see. So this would be kind of neat for somebody that was wearing this little microbit and it sensed the pulse of the runner or whoever, for whatever reason they're wearing it. And it could show you that, yep, your heart's beating. So, like I said, that's a pretty neat little device. Anyway, so those were the results that we had, that we have based on the research in the previous slides. Thank you for your time. Please feel free to ask any questions at the end of the presentation. Thank you.
My name's Anya, and I'm going to be talking about the methodologies and research of subgroup 2. Before I can introduce anything about our progress, I need to explain what a PQRST wave is. So that is a heart wave. A PQRST wave is a heart wave, and it is shown at the upper right side So there's two parts that we need to talk about for your understanding of what our team did. The first thing you need to understand is a QRS complex, which holds the highest peak, the R peak, as shown in the graph, right? And that this waveform that the PQRST has, that's what we're looking for when we filter data. It's what we're trying to make the raw data to look like. Okay, and so with this in mind, we can get started. So once we received the data from subgroup 1, we performed spectrum analysis, right? And we did this with the Fourier transform method, particularly the fast Fourier transform method, which MATLAB has. And this changes time domain to frequency domain. And this can be seen in the lower two right graph boxes that are spectrum analysis examples. Then we did filtering. We did the Butterworth filter, we did a low pass filter and band pass filter, as well as a zero phase filter. So the low pass filter is our preliminary filter, and we did this to get an idea of what the wave, where it is, what it's like. And then we did a band pass filter as well to be more exact or in the range. And the zero phase filter is to stop phase shifts, because when you do a low pass or a band pass filter, you might have a phase shift in the data. And so by using a zero phase filter, we minimize those cases. Then we created a QRS detection algorithm. And our algorithm takes two things into account: the threshold detection and the peak distances. So the peak distances, the R peak distances exactly, we know that your heart doesn't beat again until 200 milliseconds till 200 milliseconds has passed at least. So knowing this, we can use threshold testing and the distances between the peaks to determine the QRS complexes. And then last, we did a arrhythmia test, and we find the Leucian distance of pairs of our peaks. We use 3 pairs, so we use the first pair in the first 10 seconds of the data, the one in the middle, and then one at the end. And then we find the standard deviation of these peaks to determine if you have arrhythmia or not. The next thing, the challenges that we had with this was that the frequency of the device or software used by subgroup 1 was in the range which we expected the R peaks. So the frequency of an R peak is around 1.5 hertz, but as shown by the upper right graph, you can see that the frequency of the base data with no people using it already shows 1.5 frequency being used. So this made it very hard for the filtering because we don't want we don't want that. Like, you don't want that in your data, but we have to filter so that isn't considered, but we still need the heart rate. And the next thing we did, the next problem we had was filtering. Our Butterworth bandpass filter, the range doesn't work for all the test subjects. So some of the people who measured their heart wave, their frequency is below the high pass cutoff range. So the lowest cutoff range. Our cutoff range is between 0.2 and 0.5. So some of the people aren't in this range, which makes the filter need to be progressed on. And then we also did 1 minute testing samples. So that means that their analysis in their hands, the data we got, they kept their hand like this for 1 minute. And so this testing had the magnitude of the QRS complexes, and the 1 minute testing was way smaller than the magnitude in the 10-second testing. And so that is pretty insane. But we will be working to amplify those things with time. So the QRS detection that we use, since we use threshold detection, actually picks up P and T peaks, which isn't an R peak, right? So they'll pick up more peaks than needed. And so the beats per minute that we calculate in the end are greater than actuality. But our plans are to do slope analysis with other challenges in the future so that we can avoid the P and T peaks. Our arrhythmia testing needs more areas for testing. And the previous slide, I said we did 3 pairs, but 3 pairs isn't enough data as we found out. So we need to do like 4 or 5 pairs. So that's the methodology. So our results were that we were able to calculate the beats per minute and that we have a base code for the arrhythmia test. And as you can see on the right side, this is some of the code for the arrhythmia test. We find the first peak and the second peak, and then we do the Leucian distance, and then we find the next peak and the next peak, and do the same thing. And so at the bottom, we have a picture of the beats per minute calculations on the seconds that we had to do those peaks as well. So as you can see, these heartbeats per minute are pretty high. And this is because in the example code, it picked up the P and T waves, the P and T peaks. So the beats per minute are higher than it should be for sitting resting. That's it for the result of subgroup 2. Now we'll move on to subgroup 3.
Hi, my name is Funmi, and I will be talking about the methods involved in developing our Android application. We initially compared different IDEs to find the most efficient development environment for Android application, and we concluded on using Android Studio because it was most efficient in the sense that it met our project goal. It involved downloading less components than other IDEs we came across. Next, we created a user design experience to test, research, and develop our Android application for quality results on Adobe XD. We used Java and XML on Android Studio to design the Bluetooth interface to retrieve filtered data to be displayed on the application. And we also tested the Bluetooth connectivity using an emulator and an Android phone. In the absence of the Bluetooth module, we took an alternative route, which involved graphing a CSV file received through an email on the mobile app. The application had two main views. The first view included button options to turn Bluetooth off, get paired devices, and to show visibility to other devices. Once these devices were paired, this page showed these devices, and the final view displayed the test signals received in the CSV file.
Hello, my name is Precious, and I'll be talking about the software aspects and the challenges we faced during this project. Number one was finding the right integrated development environment. First of all, we used Eclipse. In Eclipse, we saw that there was a lot of difficulties in downloading the application. First, we didn't have enough space using MacBook, and we saw that we won't be able to work using this IDE, so we moved over to Kiwi. Kiwi, on the other hand, we use Python. It's a Python-based application. So my partner, unfortunately, doesn't know how to use Python. So we had to, compromise and change it over to Xcode. On Xcode side, we were proficient in using it, knowing that we have used Waveland C++, and my partner is proficient in it. But we found out that the Bluetooth device module we'll be using will be dealing with Android applications and cannot be using an iOS. So we had to switch it to Android Studio, which was a challenge in my own ends because I've never used Java before. So we were able to do some research and dig in and able to create an application using the Android Studio. Another application we used in designing the user interface was Adobe XD. In Adobe XD, as you can see on the right, you can see that we did the design of the UI on the right and how it was supposed to look like. Then we came into the Bluetooth connectivity on the Android using Java and XML. We are having difficulties in connecting to Android application with our Bluetooth device. So we were able to rewrite the code and graph it both together using the activity box in Android Studio, and also we were able to make the two Android devices connect together. Another challenge is using the micro:bits. Unfortunately, we got this micro:bits at a very late pace, so we couldn't be able to use the micro:bits. But in the future time, we'll be able to learn more of this micro:bits, or if we have time, or if there's more resource in getting the HC05 Bluetooth module, we will be using the HC05 or micro:bits to be able to receive data, filtered data from the subgroup 2, which are the filtered data that will show our filter out the sounds and be able to show our real heartbeat, and to be able to calculate the beats per second if we were able to use the micro:bits and the HC05. Thank you very much.
Okay, I'm back to talk about lesson plans and what we've come up with. So concept that was developed, concept development, or our thoughts behind this are going to be, basically we're going to start I'm going to start in my classroom, and these can be tailored to any secondary education facility and beyond. Just some thoughts and stuff. So the first one would be covering IV characteristics curve. It's what we did here during the research process. And it was, we did learn a lot. This allowed us to incorporate the analog discovery, some components. So it'll be a good start for the second year students I believe. So basically the IV characteristics curve is going to, we'll be able to show the relationship between current, voltage, how they work together. And, you know, without one, you can't have the other. So it'll be an interesting topic. The next one, I took one of the circuits that we built using the analog discovery to learn how to use it, and that was the voltage divider. So it's an analog circuit, and it will be a great introduction to basic electronics. And again, just build off of the IV characteristics curve. So the next one, the next lesson plan that I think will be interesting is also the digital circuits. So since we covered we researched using an op-amp, why not incorporate it into the lesson plan? So op-amps are unique. They're used in electronics all over the place. So this was a fairly easy circuit to build. I'm not sure about teaching it, but because there's math in it, and nobody usually likes to do math when I teach it. So op-amps. So op-amps, again, it's an integrated circuit. It's an IC chip, and it can be used in many ways. So it'll be a nice addition to the digital circuits module that I teach. Of course, all the lesson plans or anything that is taught in engineering, science, technology, and math, it's really easy to relate it to STEM. And so for me, the STEM focus is what I try to work on and introduce to students. So it makes it fun. There's a challenge usually, but they learn more than just circuits or components or electronics. It can be incorporated into anything. And so to touch on that more, STEM, Arduino, microbit coding, you can take these little projects. There's also activities to use the microbit and the Arduino to build games that, you know, we used to play as kids. Operation. There's a nice little tutorial on how to build something along those lines and code the microcontroller. And so it's a good focus. It's entertaining and usually keeps the kids engaged. So all the lesson plans will be scaffolded. So they will start baby steps, crawling, walking, and then hopefully running without anybody tripping in between. So what they'll do is they'll build off the previous lesson, and at the end, it'll be a culminating lesson, and hopefully all the objectives will be met at the end through the scaffolding method. It will include instructional methods that any teacher will be able to use. They'll be using the direct approach method, which is a quick teacher instructional time, so that you show them exactly what you want them to do, and they learn from that. You're not spending a whole lot of time in the classroom doing that. You do the direct approach, teach them what you want them to learn, and let them go. You walk around, observe, give guidance, and talk. And then the other is student-led. Student-led is sometimes a good option depending on the project and depending on how many you group together. Usually more than 3 is chaotic, and unless it's a project that requires a lot of people doing it, not recommended. And then just for all the lesson plans, the overall goal is to introduce new concepts, ideas, career paths, and basically to prepare the learners for their transition into out of high school and into some type of career, whether it's college, whether it's a technology or anything like that.
Hello, my name is Adam Bohack. I'm here presenting the activities associated with the STEM curriculum for the high school program. As we all know, many high school students do not come prepared with their skill and knowledge development in electronics and coding. So for this, in order for them to accurately and successfully complete a project of this magnitude, we have to build that skill and knowledge up. And there are several activities incorporated within the lesson plans that were previously mentioned that will allow students to build their skill and development through scaffolding activities, hands-on projects, and other resources that are available to us now. In order for students to understand how to completely work with a project such as a heart rate sensor, they have to understand the coding behind the Arduino board. So in order to start with that, we want to build their skill and development with basic coding knowledge. And there are several activities associated with that that start them off with very easy, basic steps and develop their skill and to incorporate harder, more rigorous projects. And those would include the turtle drawing application, basic math problem statements, basic if-else statements, and basic loop statements. Once students have developed a basic understanding of the coding language, they can move on into more complex Arduino projects that take this idea of coding and apply it to a circuit project where you can kind of manipulate the circuit a little bit more using a coding language and the Arduino board. And those projects would start off with a blinking light. And then as students understand how that blinking light works, they would advance into a traffic signal, for example. And as students understand how a basic traffic signal works, then they could incorporate an entire traffic intersection with interrupts such as a stop walk sign for pedestrians. As students have once students have gotten through the basic Arduino projects that are supplied to us, they can move on to incorporating the Diligent Analog Discovery Kit in order to use that as a measurement device in order to not only supply power to their board. In certain cases, most schools don't have the necessary equipment in order to supply full power to a circuit board. The Discovery Kit allows us to power our circuit board while simultaneously acting as a measurement device, whether it's a DC circuit measuring the voltage drop across a component or using it as an AC source and developing the waveform that's associated with that so they can analyze the waveform that's generated. They would apply that knowledge to finally working on a project of this magnitude where not only do they have to develop a circuit that includes advanced circuit design such as op amps, joule filters, and such IC chips like that, they'd also have to include the waveform of the Diligent Discovery Kit in order to see the waveform that's generated by the piezo sensor or a photo sensor. And once they have all those pieces together through these scaffolding activities, they would be able to successfully complete a heart rate sensor using either a photoresistor or a piezoelectric sensor.
Hi, my name is Alvin Nabwe, here to discuss with you guys about our future plans concerning this project. We hope to develop a fully encompassed monitoring system that incorporates a wristband with the piezoelectric sensor, PDF. This wristband will hold a similar display to the Apple Watch or the Fitbit. This display will sync via Bluetooth to a smartphone application that will collect data, record data, and sync the data to a primary care doctor for monitoring and keeping health records. We would also like to expand on the data collected by the wearable sensor, add additional sensors and technology which will be used to do more things than just read the heart rate, like check on your breathing, check on your other organs, and anything with the system, anything the monitoring system could do. We're trying to get the wristband to act as the monitor, make it more mobile, hopefully easy to come by, and also easy to use. In addition, this project will be added to digital electronic courses in the high school curriculum, also electronic courses in the college school system. The Bluetooth module could be used in the mobile application to acquire heart rate data to display information for different smartphones, making it easier for more people to use it and hopefully more frequently. That's it. Thank you very much. Any questions?